In Chapter 20 we discussed expected values. Expected values can be thought of as the average value of some random phenomenon over the course of a long sequence of trials. These are the concepts that we will discuss in Chapter 20. Expected values, the law of large numbers, thinking about expected values, and finding expected values by simulation. Let's begin with an example. In a simple pick 3 lottery game, you pay 50 cents and choose a 3-digit number. The state then selects a 3-digit number at random and pays you $250 if your number is chosen. As there are 1,000 possible numbers, you have a probability of 1 in 1,000 of winning. Here is a probability model for your winnings. Note there is a 999 out of 1,000 probability of winning nothing. Now if one played this game many times, what would their average winnings be? Because we make $250 every time we match, and this occurs about 1 in 1,000 times, we would expect to make 250 times 1 over 1,000, or 25 cents, in a long sequence of games. Here is a general definition of the kind of average outcome that we discussed in the previous example. The expected value of a random phenomenon that has numerical outcomes is found by multiplying each outcome by its probability and then adding all the products. In symbols, if the possible outcomes are A1, A2 through AK, and their probabilities of occurring are P1, P2, all the way through PK, then the expected value is equal to A1 times P1 plus A2 times P2 all the way through to AK times PK. An expected value is an average of the possible outcomes in which each outcome is weighted by its probability, so that outcomes that occur more often get higher weights. Let's do another example. Here we again have a lottery game where we choose a 3-digit number. However, this time we win $292 if we match exactly, and we win $42 if the selected number is a different permutation of our number. For instance, if our number was 123, then we would win $292 if 123 is selected. We would win $42 if 132, 213, 231, 312, or 321 is selected, and we would win $0 otherwise. The probability model for our winnings is as follows. Using the definition of expected value, we see that our average winnings over the course of a long sequence of trials is $292 times 1 over 1,000, plus $42 times 5 over 1,000, plus $0 times 994 over 1,000, giving us an expected value of $0.502, which is about 50 cents. Now you try one. Below is the probability model for the number of children under 18 for American families in 2009. In the table, 4 represents 4 or more, but assume that it means the family has exactly 4 children under 18. Use this model to find the expected value for the number of children for a randomly selected American family. So pause the video and unpause when you're ready for the answer. Recall, using the definition of expected value, we multiply each observation with its probability and then sum the result. If we do that, we see that the expected value is 0.82. The definition of expected value says that it is an average of the possible outcomes, but it's an average in which outcomes with higher probability count more. The expected value calculated from a probability model really is the long-run average. This fact is called the law of large numbers. According to the law of large numbers, if a random phenomenon with numerical outcomes is repeated many times independently, the mean of the actual observed outcomes approaches the expected value. The law of large numbers says that the actual average outcome of many trials gets closer to the expected value as more trials are made. It doesn't say how many trials are needed to guarantee an average outcome close to the expected value. That depends on the variability of the random outcomes. The more variable the outcomes, the more trials are needed to ensure that the mean outcome is close to the expected value. We can also use simulation to estimate expected values for situations where the expected value is difficult to compute. Recall, to perform a simulation, we first give a probability model. We then assign random digits to outcomes, and finally use a table to simulate outcomes. By the law of large numbers, the average outcome of these repetitions will give us an estimate for the expected value. Let's recall the example in Chapter 19 of the couple who decided to have children until they either had 3 or a girl, whichever came first. How many children on average will couples who follow this plan have? To try and answer this question, we will use a simulation. The simulation is set up just as before. The digits 00 through 48 are assigned to girl, as there is a 0.49 probability of having a girl, and the remaining digits will be assigned to boy. We also assume that the sexes of successive children are independent. Here are the 10 repetitions we used in the example from Chapter 19. We will keep track of the number of children in each one. If we add the number of children in each of these 10 cases, then divide this sum by 10, we get an average value of 1.7. This is our estimate for the expected value, as given by the law of large numbers. It turns out that the true expected value is 1.77.